Yeah, so
Okay. So
let me first introduce, of course, Andrea Santi from Tromsø University, Tromsø, but also it's called the Artic University of Norway. Yeah, so I don't know that what is the, I mean that's the Artic University of the Norway is a more official name, and Andrea Santi only visits the Czech Republic many times. Had collaboration is many people from our group, so I don't think that that we don't. I need to introduce Andres more. Only via Zoom, yeah, and today I'm on G3 supergeometry and equation. Yes.
Okay.
Please,
Thanks.
Andrea.
I did hear you not perfectly well, but please let me know, guys, if you have any problems with hearing me. So first of all, thanks for the invitation. And the talk today is devoted to geometric realization of the simple Lie superalgebra G3 of dimension even 17 and odd 14 as symmetry superalgebra of various geometric structures, in particular differential equation in superspace. The plan of the talk is first, I would like to give you a quick introduction to Lie superalgebras and supermanifolds. Perhaps these are not familiar to everyone. And I will recall some various realization of the exceptional algebra G2 as a symmetry algebra. Then we will move to the super case, and I will discuss first algebraic aspects and parabolics of algebras of G3, and focus on two of them, for which I will explain how to compute Spencer cohomology. And then we will arrive at the geometric realization of the Lie superalgebra G3 as supersymmetry of differential equation. The part on curved G3 supergeometries, let's see if I will have time. I believe it was a bit too ambitious, so let's see. But in a case, I will also discuss some curved version of the story before. So this is joint work with Boris Kruglikov and Dennis D, and it has recently appeared on Advances in Math. So if you are interested in knowing more details, you can have a look at the paper. Okay, so let me recall you first of all what is a Lie superalgebra. So this is a, say, complex vector space endowed with the decomposition into even and odd part, and it has a Lie bracket. So the Lie bracket has to satisfy certain axioms. It has to be compatible with parity. So for example, if you do even, you end up in even, and similar for the others. And then that's the general rule in superalgebra or in supergeometry, that whenever you have an equation and certain terms are interchanged, a classical equation, then in the supersetting, it acquires an extra minus signs if both elements are odd. So for example, skew symmetry, it's still skew symmetry if either X or Y is even, but if both elements are odd, then actually the bracket is symmetric in a Lie superalgebra. And similarly, the Jacobi identity will acquire extra signs. The finite dimensional simple complex Lie superalgebras were classified by Katz in '77, and they split in two main families. The classical one, for which the adjoint action of the even part on the odd is completely reducible, and the so-called Cartan Lie superalgebras. They are called in such a way because they are analogs to the primitive simple Lie algebras of vector fields introduced by Cartan. Inside the classical, you have in turn those which are as close as possible as Lie algebras, in a sense that you have root systems and all the machinery that you have for simple Lie algebras. So you have the SL series for matrices with zero supertrace, the orthosymplectic series, which encompasses the orthogonal and symplectic series together. And for special values 4 and 2, the orthosymplectic 4-2 algebra actually admits a one-parameter family of deformations, which are still simple Lie algebras. okay? So then we also have another two exceptional cases. One, it's sometimes called F4, but it's a bit confusing with the classical case. So I'll call it F31. And then we have what is the main object of interest for us today is G3. So its even part is G2 and SL2 acting via the standard representation of G2, tensor C2. So there's not much hope to find a linear realization of the one parameter family of orthosymplectic for 2 and the other two exceptional Lie algebras as a symmetry, as linear symmetry of some simple geometric object. Essentially, one of the reasons behind this is that they suffer from the same pathology as of E8. The smallest non-trivial representation is the joint representation. So we got interested in describing these 3D superalgebras as symmetries of nonlinear objects, and we have done this for G3. And that's what I'm going to tell you essentially today. So let me recall you also what is a supermanifold of dimension Mn. So that's a pair given by a classical manifold of dimension M and a sheaf AM of superalgebras such that locally it's identifiable with a sheaf of sections of the exterior power of some vector bundle of rank n. So if you think about sections of the structural sheaf AM, they emit an analytic expansion in the odd coordinates. So here the theta's are generators of the bundle, and F, you can write it as F0x, where X is just our point on M0, plus another function theta alpha 1, and so on and so forth. And you stop at alpha theta alpha 1 wedge theta alpha n. Of course, these odd coordinates anti-commute, so in particular they are nilpotent, and if you consider the natural evaluation map that sends your super function f to f0 of x for any fixed point x of m naught, then the thetas are sent to 0. So super functions are not determined by their values at points. So that makes the theory of supermanifold in a way closer to algebraic geometry than to differential geometry. But still, a lot of concepts of differential geometry carry on. In particular, one can define superdistribution on M as a graded AM subsheaf of the tangent sheaf, which is the derivation of AM that is locally direct factor. So I'll give you two examples here. So consider C 5, 2, so with 5 even coordinates and 2 odd coordinates theta and u. And consider the subsheaf of the tangent sheaf generated by the super vector fields here. This is a honest super distribution of rank 2, 1. This is a super extension of the natural Cartan distribution associated to the Hilbert-Cartan equation, but we will be back on this. So for the moment, just consider it as an example. If you consider this as if you consider the derived sheaf of the super distribution, so you start adjoining brackets to the distribution you have started with, you will discover that you will get a vector field which is theta du. So it means that this derived sheaf is generated by super vector fields that are linearly dependent, because of course you can multiply theta du by theta itself, and theta squared is 0, and you get 0. So the second example is not a super distribution, and it's kind of degenerate example which we don't consider in our setting. Okay, so let's go to some classical realization of G2. So we are all familiar with the description, abstract description in terms of thinking diagrams. So what about realization as symmetries? One of the first realization was discovered by Engel at the beginning of the previous centuries. He studied the action of the general linear group on 3 forms in 7 dimensions, and he realized that stabilizer of a generic element is isomorphic to G2. Later on, Cartan told us that the compact form of G2 is the automorphism of the tonions, and similarly for the split parts. More recently, configuration space of a two-sphere rolling onto another without twisting or slipping was realized to be tightly related to G2. So this configuration space is 5-dimensional. And the constraints given by the absence of twisting or slipping is a non-holonomic constraint. So it's encoded by a rank 2 distribution D of filtered growth 2 to 5. Filtered growth, I mean that if you consider the distribution, the rank is 2. If you adjoin brackets, you'll get something of rank 3. And if adjoin brackets of brackets, you will end up spanning the full Dungeon space at a point. So this is true actually if the ratio of the radius of the sphere is different from 1. Generically, the symmetries of this configuration is just SO3 and SO3, just rotating individually each sphere. But for a special value of the radius of the sphere equal to 3, then the symmetry is enhanced. And the automorphism of M and this distribution has been realized and then further studied by many authors to be the split form of G. Okay, so from the modern perspective, this homogeneous manifold is G2 modulo the parabolic corresponding to declaring the first simple root having degree 1 and the second simple root having degree 0. So that I'll call it the parabolic P1. And here you can see these two simple roots in the root diagram of G2. They have degree -1. If you bracket them, you'll adjoin these elements, so you'll get something of dimension 3. And if you further bracket, let's say, this element with this, you'll get this one. And similarly, this one, so you'll get something 5-dimensional. So this has to be thought to be as the tangent space at the fixed point of our flat manifold, and the red part is the stabilizer given by the parabolic. Curved version of these flat models, rank 2 distribution in a 5-dimensional manifold, generic ones. In modern terms, the fundamental invariant of this curved object is a binary quartic field. So this was actually already discovered by Cartan in 1910. But the modern perspective is that this invariant arises from the Spencer cohomology group of MG. So that's the Chevalier-Eilenberg cohomology of the Lie algebra M, which is the negatively graded part of the 3 grading of G2, as I just explained, and G is just the whole G2. Here, the 0-degree component, if you want to read out the 0-degree component of this regrading here of G2 is this piece here. You'll have these 2 roots, and the center corresponds to the 2-dimensional subalgebra. So that's GR2. Some further geometric realization of G2. So one was discovered by Engel, and he realized that G2 is the symmetry of a contact distribution of a 5-dimensional manifold, and now with an additional structure. So a field of twisted cubic inside the projectivization of the contact distribution. I will not say more on this because I will explain the super version of Engel construction in more detail later on. Then there are other 2 realizations of Cartan. So one is this system, overdetermined system of PDEs. So U is your dependent variable that depends on X and Y, which are independent. So this, you can think of these PDEs as an appropriate submanifold in jet space. And Cartan realized that the symmetries of these submanifolds are, in an appropriate sense, are exactly G2. We will also generalize these equations, so I'll give more details later. And the other one is the celebrated Hilbert-Cartan equation. So here, X is the dependent variable, and Z and U are dependent. The Hilbert-Cartan equation is the undetermined ODE Z prime equal U dash dash square.
Andrea,
Yeah.
Yes, it's a famous this equation, Hilbert-Cartan equation. I mean, that's I read something like that, but the history why that is these are two guys interested and that is so famous.
White, sorry, I didn't hear very well. So why this equation is so,
yes.
Yeah,
this
it was
equation
discovered
is,
by. Well, it was one of the first realization of G2 as symmetry of a very simple object, because Z prime equal.
So that is that's a Cartan working with the Lie algebra. I understand, but why Hilbert?
Why Hilbert? He later on studied this equation, and yeah, so it also bears the name of Hilbert, but it was discovered by Cartan.
So that first discovered by Cartan because he considers it a G2, yes, and then Hilbert reconsider it, yeah.
Hilbert reconsidered it, yeah, and proved for further results, yeah. So let me give you a bit more details about this equation. So consider jet space, mixed jet space, depending on one independent variable x, and u and z, which are dependent variables, and you consider derivatives of u up to second order and of z up to first order. So in this mixed jet space, you have the natural Cartan distribution, which is the kernel of this Pfaffian system. That's a very natural Pfaffian system. It just tells you that u over dx is u dash, and so on. So the Hilbert-Cartan equation cuts out a 5-dimensional submanifold in this jet space, and you can endow it with a distribution as well, which is nothing but the pullback of the Pfaffian system above. The distribution on this 5-dimensional submanifold is generated by as rank 2 and is generated by the following two vector fields. That's just the truncated total derivatives with respect to x, and then the partial derivatives with respect to u double dash. If you consider the weak derived flag, as I said before, you consider D, then you adjoin brackets, and then you adjoin brackets of brackets, you will realize that this has growth truthified. More precisely, passing from the filtered to the graded level, you get a symbol algebra, which is a Lie algebra, and the symbol is exactly the negatively graded part of the T grading of G2 I explained a couple of slides ago. So this is you can think of this as our flat model. So this is a 5-dimensional manifold, homogeneous for G2, and the distribution is the one that I explained before in terms of root system in an invariant way. Okay, so general motivation. We wanted to give realization of these 3 exceptional superalgebras, symmetry superalgebra of some simple geometric objects. On a more general level, we are interested in geometries that have high symmetry, a lot of solutions to BGG equation, Killing-Spinor equation, and so on. And we plan to understand the relationship coming from symmetries of superdistribution and solution of PDEs. Another interesting point is the following question. Does any given classical geometry admit a non-trivial supersymmetric extension? So far, we studied G3, so we gave various geometric realization, which I will explain, and we understood the deformation of these flat structures. Okay, in particular, I'll exhibit some super extension of the Hilbert-Cartan equation, and if times allow, some non-flat super extension of 2-3-5 geometries, and give some bounds on the supersymmetry dimension. Okay, let me recall you a bit about the structure of G3. So you can fix a Cartan subalgebra H in the even part, which remember is G2 and SP2. Since there will be a lot of SL2 subalgebras lying inside G2 in the next slide, when I use the notation SP2, I will also always mean the ideal in the even part of G. So you have a root system which splits into even and odd roots. The Killing form is non-degenerate, so that gives you non-degenerate pairing on H star.
Andrea, actually, I never know this superalgebra G3. So you say that is of course because the superalgebra is G2 graded, right? But of course and the G0 is an extension of G2 and the SP2, yeah.
Yeah. So G3 is usually defining given the even part, G2 and SP2.
SP2, yes.
The odd part, and then usually it's introduced by explicitly giving the brackets. So it's not nicely introduced as symmetries of anything. Okay, if you pick up an even root, then this is necessarily non-isotropic, and you can consider even reflection as in the classical case. They preserve both even and odd roots. The Weil group is generated precisely by these even reflections. One difference with respect to the classical case is that up to equivalence by the Weil group, there's not only one simple system. In this case, you have four of them. And how can you pass from one simple system to the other? That's via odd reflections. So in your simple system of roots, you may consider an odd root. This can be either isotropic or non-isotropic. If it is isotropic, then you have a recipe that allows you to reflect all betas which are in your simple system and obtain another simple system which is not equivalent via the Weil group. So in our case of interest, these are the four simple systems. These nodes here, the white one, are as in the classical case. So these are even non-isotropic roots. Wherever you have to differentiate it for odd simple roots, isotropic is a gray node and non-isotropic is a black node. So here in this red arrow, you see exactly what it means to apply an odd reflection on a non-isotropic group. This number above here are the Dinkin labels, so they tell you what are the coefficients of the highest root with respect to the fixed simple root system. Okay, so if you want to describe all parabolics, you have to take into account all four simple system, and you arrive at the following map of flag supermanifolds for G3. So the notation is that, for example, here M13, it means I'm considering the third Dinkin diagram with the first simple root declared to have degree 1 and the other two simple roots having degree 0. So the flag supermanifolds we studied is exactly this little triangle here. Okay, so this grading over here, it's also M14. It means I consider the fourth Dinkin diagram, which is this one, and across the first node. And we call this grading G3 contact because it extends the contact grading of G2. If you forget about the odd dimension, this little 4 here, you'll get dimension 4, 1 of G-1 and G-2. That's exactly the contact grading. So this is enhanced in -1 degree by a 4-dimensional odd subspace. This other grading here, we call it super Hilbert-Cartan. So it's the associated flag is M24. It means fourth Dinkin diagram, second simple root crossed. And indeed, if you forget the odd dimension, this 4 and this 2, you'll get 2, 1, 2. Before I said 2, 3, 5, because it's customary to refer to the filtered growth, and I didn't want to use a different notation. But that's exactly what we have. 2 plus 1 is 3, and then you get 5. Okay, so the graded growth is 2, 1, 2 in the even part, and that's exactly the 3 grading of G2 I explained before. It's enhanced in the odd part by a 4-dimensional and a 2-dimensional space here. Okay, any grading of G3 is symmetric, so that follows because the Killing form is non-degenerate. So some few more details about these two grading, the G3 contact and the super Hilbert-Cartan. In the G3 contact, the 0-degree part is given by the grading element, and the subalgebra F, which is isomorphic to orthosymmetric tree 2. You can easily read off from the thinking diagram here. You will remove the part with the cross node. You will remain with this thinking diagram here, and that's precisely orthosymmetric tree 2. If you do the same thing here, you will remain with SL2 and with this single black node, which is orthosymplectic 1, 2. So the even part is this plus the grading element. Okay, let me immediately tell you the results, and then I will comment on how we obtain them. So these are geometric structures associated to this flag supermanifolds for G3. So the first one, we call it G3 contact super PDE. It's an extension of this overdetermined pair of PDEs here. And the part in blue is exactly the equation we had before. But now U, it's still single, it's still valued in C, but it's also has two odd variables, ni and tau. And the equations are pretty different, okay? So you can consider them as a super extension of the PDE system we have seen before. I would like you to draw your attention on this last equation here. It tells us that U, Y, it's not really our fundamental object any longer, but it's further constrained. It has to be the opposite of U derived along the two odd coordinates. Then we got the super Hilbert-Cartan equation. In this case, similar to before, the codomain is unchanged, but U and Z do not depend just on X, but on two additional odd variables, which are ni and tau. The part in blue is the Hilbert-Cartan equation. And also in this case, UXX is proportional to U derived along the two odd directions. So we obtained these PDEs here in superspace and shown that they have symmetry superalgebras G3. So what's the strategy? It involves some cohomology computation, and since this is that's I think a topic of interest for this seminar, so I decided to spend a little more time on how we computed this cohomology. I believe some of the techniques can be adapted to different contexts and could be useful. So so the idea is that one wants to understand, given a negatively graded Lie superalgebra M, and possibly a subalgebra G0 of the 0-degree derivations, one wants to understand the so-called Tanaka-Weisfeiler prolongation of MG0. So this object is the graded Lie superalgebra that satisfies the following three properties. So the non-positive part has to coincide with M plus G0 as a Z-graded Lie superalgebras. Secondly, you don't want in positive degrees to have anything that is not visible. So here actually I didn't say it explicitly, but usual requirement is that M is generated by the minus one part. So this second requirement tells us if you have X of positive degree, and it acts trivially on everything on degree -1, then actually X has to be 0. This prevents you to add things in positive degree that could be in the center of, for example, of your Lie superalgebra and are completely unreasonable. And third property, this Tanaka-Weisfeiler prolongation has to be the maximal one that satisfies properties 1 and 2. If G0 is the full algebra of 0-degree derivation, then sometimes we simply write prolongation of M instead of prolongation MG0. So the relevance is that the Tanaka-Weisfeiler prolongation is the symmetry superalgebra of the natural geometric structure you have on your standard model. So on exponential of M and the distribution, left invariant distribution corresponding to G-1. Possibly with some reduction of your structure group if G0 is a proper subalgebra here. Although this prolongation can be defined and also obtained via an iterative process, this is a difficult way to get the prolongation. One can test a candidate G that extends mg0 with the following criteria. G is the prolongation of M if and only if the first Spencer cohomology group in non-negative degrees vanishes. G is the prolongation of mg0 if and only if the first Spencer cohomology group of mg in positive degrees vanishes. In the classical setting, one has the constant version of Borel-Weil theorem that efficiently computes this cohomology group in terms of harmonic cohomology. But in the super setting, is well known that these harmonic cohomology is usually bigger. So this very important machinery is not available, and one has to follow different routes. In the case of the G3 contact gradient, we use the Hochschild cell spectral sequence, a kind of standard tool. For the super Hilbert-Cartan, that was still too complicated because the depth is 3. It becomes too involved, and we have to resort to a different strategy. And that's what I'm going to explain now. So there is a very useful relationship between the Spencer cohomology groups of G and classical constant cohomology. So consider here lambda nm star and the restriction map to elements of the even part of M. Okay, so this is a short extant sequence, and I'll denote by K the kernel of this sequence. So here, the exterior power, since M is a super vector space, it has an even and odd part, is meant in the super sense. So if both elements are odd, they actually commute instead of anti-commuting. Okay, then you may tensor this sequence with G, and this gives us a short exact sequence of differential complexes. So in the middle, you have the Spencer complex. Here you have the complex of the Chevalier-Allenberg complex of the algebra M0 with values in G. And here, with a little abuse of notation, I'll denote it by C-bullet M odd G. That's the subcomplex of the Spencer complex given by the cochain that vanish when all entries are in M even. So every morphism in the sequence is equivariant by the even part of G0, which I recall you is grading element, SL2 inside G2, and SP2, the ideal in the even part of G3. So the associated long exact sequence in cohomology gives the following long exact sequence here. Sorry, I repeated myself. The point is that here you have this cohomology group M1G. These are the cohomology groups we are interested in, and these are cohomology groups for M0 with values in G. Here you have the component of Z degree D of the centralizer of M0 in G. So what's the general strategy? So our goal is to obtain these guys here. So one can describe this cohomology group here using a constant. Remember, for us, M even is the negative part of the 235 grading of G2. So that's an honest framework where we can use constant. Then you need to put some extra work and compute explicitly this group here. For the second Spencer cohomology groups, it's rather involved, but it's still doable. And then you get this group here using the long extant sequence, and also using the fact that this module here, unlike this one and this one, are modules for all of G0, not just the even part. So in particular, they are module for orthosymplectic 1, 2. So let me give you first the result and then the details. So consider the super Hilbert-Cartan grading of G3. Then the first Spencer cohomology group vanishes in all non-negative degrees. So for the criterion I have explained before, that tells us that G3 is indeed a prolongation of M. So you, first step, you consider the Bott-Borel-Weil theorem for this group here. So you need to compute these cohomologies for M even with values in G2 in the trivial representation and the standard representation. And most of them are 0, except one contribution in degree 1 here and a contribution in degree 0 here. This is completely standard. One can use constant machinery. So remember, in the G3 is this guy here. So as a G2 module splits into adjoint, this is a sum of trivial modules, and this is a sum of a standard representation. So we computed the cohomology here. You put all of things together, and you will realize that the only contribution that are non-trivial on this part are in degree 0 and in degree 1. Okay, so using this and computing explicitly the centralizer, which vanishes for all positive degrees and in degree 0 is sp2, you arrive at the following 3 x-dot sequences. Okay, so the input is these 3 pieces here, which we computed at the first step, and this sp2 and the 0 here, which are the centralizers. So the second step is to compute explicitly this cohomology group here by hand. So you do that, and you discover that they vanishes except in degree 0, which is isomorphic to sp2. So for example, here, if the degree is strictly bigger than 1, this is an exact sequence. So you will discover that your Spencer cohomology group in degree strictly bigger than 1 already vanishes. In degree 0, this has to be an isomorphism between these two. So H01Mg is either 0 or all of this by irreducibility. And similar for H11 is either 0 or all of this. So to conclude the proof, we want to exclude the possibility that that these two groups are non-zero. Okay. If you try to do this by hand, it's doable, but it's still not very illuminating. So remember that these two groups here are module not just for the even part of G0, but for all of G0. In particular, they are modules for orthosymplectic 1,2. And by result of Djokovic and Hochschild, the representation theory of orthosymplectic 1,2 is reasonable. Representations are completely reducible, and any non-trivially reducible representation decomposes under sp2 into the direct sum of 2 irreducible sp2 modules with different and consecutive highest weights. But that's not the case here, right? Here, with respect to sp2, we have 3 copies of the standard rep, and here we have 2 copies of their joint. So they do not have consecutive highest weights. So without even computing anything, that will tell you that that these two groups here do actually vanish. Okay, so let me skip the computation of the cohomology group for Spencer cohomology group of second order. If I have time, I'll be back on this. Okay, so our goal was to find model with the desired symmetry. So in the classical case, one can start, for example, with the 2-3-5 symbol algebra, integrate the structural equation, perhaps using Baker-Campbell-Hausdorff formula, to arrive at the local model, which is equivalent to the Hilbert-Cartan equation. We first obtained super Hilbert-Cartan equation also in this way, but it's too involved even to be presented, so we follow a different and more conceptual route, which I will explain. Then one would like to prove that this homogeneous model has the expected symmetry dimension. The Tanaka-Weisfeiler prolongation via the resultant Spencer cohomology, first Spencer cohomology group, gives our upper bound. since in the supersetting we are working on it, but there's still no well-developed theory of parabolic supergeometries and harmonic curvature, one doesn't have a test for flatness as his disposal, and that meant that we needed to compute symmetries explicitly by hand. So the general strategy is the following. We consider this double fibration of G3. Here on the left, you have G3 contact, and here on the right, you have super Hilbert-Cartan grading. And on top of that, you have the so-called correspondence space, which has a bigger dimension, and it projects on both of these two. You can obtain it by crossing the nodes that you can find on the bottom, crossing both of them. So the strategy is to follow this route here. So we start with G3 modulo P1, which is a contact supermanifold, and it has a reduction of the structure group. If you remember, I said that the 0-degree part was conformal orthosymplectic 3-2 that sits properly inside the conformal symplectic orthogonal transformation of G-1. So the idea is to realize this reduction of structure group geometrically, and we did this, we'll explain in a moment, as a 1-2 twisted cubic inside, so an appropriate supervariety inside the projectivization of the contact distribution. Then we'll look at the affine tangent spaces of this twisted cubic, and I will explain, and this is a procedure that allows to go up here and get the super PDE system, which I call epsilon, which is G3 modulo P12. This super PDE system, you may consider the associated Cartan superdistribution, and this has a Cauchy characteristic. So you want to quotient by these Cauchy characteristics, and this allows you to go here. So you follow this route in this way. And what you get at the end of the story is the super Hilbert-Cartan equation. So what are the details of this construction? So first of all, my reduction of structure group is a maximal reduction. I mean that G0 is a maximal subalgebra in conformal symplectic orthogonal transformation. You can see here that -1 is S3C2 and C2 tensor C2. So if you fix X and Y basis of this C2, this will be your basis of S3C2. And if you fix E and F basis of this C2 here, you will get the basis of -1. So this allows to make explicit the conformal symplectic orthogonal structure on G-1, which I denote by V from now on. So I want to focus on the action of the 0-degree part on the -1 part. So you may consider...
Andrea, ask a question. So computing maximum subalgebra, you can find the Dunkin classical rule on the...
No, you cannot use it because the even part is not a maximal subalgebra in the even part of... So if you look at this inclusion relation at the level of even parts, that's not maximal.
Yeah.
So you need to take into account the action of the odd part. That's crucial to prove maximality.
Yeah, thank you.
So you may consider the line through the IS weight, and if you consider the stabilizer of this line, that's also parabolic inside orthosymplectic 3-2, given by this cross-linking diagram here. It's a one grading, so here in degree 0, remember the rule, you remove, you forget about this cross, so this is orthosymplectic 1-2 plus the grading element. And here in degree -1, you have C12, the standard action of orthosymplectic C12. So I'll denote by Y1 the even generator, and A5 and A6 the odd generators. So what is the 1-2 twisted cubic? That's defined as the G0 orbit through the line of the IS weight. So that's clearly G0 invariant, and it's not invariant by all the conformal symplectic orthogonal group. So by maximality, the super variety has the property of characterizing precisely the reduction of your structure group. If you want to describe this variety explicitly, you may exponentiate the action of Y1, A5, and A6. You do this formally. You have to take into account that your parameters might be even and odd. If you are familiar with supermanifolds, you will probably know that this can be done at a rigorous level using the functor of points. If you're not familiar, you might think of this expression as fixing your preferred finite dimensional supercommutative superalgebra A and picking the parameters from this superalgebra. So lambda will be an element of A0 and theta and phi will be elements of A1. Okay. Okay, so if you repeatedly apply f minus 1 to the line passing to the highest weight, this will give you a sequence of affine tangent spaces. So V0 is one-dimensional, it's just the line through x cubed, and then you get V1, V2, and V3 will be all of V. So the crucial point is that V1 that sits inside V, which I remember you is C44 with the natural conformal symplectic orthogonal structure, is Lagrangian. In particular, it has dimension 2, 2. So let me skip for a moment also these two slides and finish this construction. So remember, these were our goals to arrive at these equations, G3 contact super PD and super Hilbert-Cartan, and to prove that they have symmetry superalgebras. Okay. As an aside, let me mention that unlike the Hilbert-Cartan equation, whose general solution depends on one arbitrary function of one variable, super Hilbert-Cartan are much more constrained. One reason is exactly this equation here. And one can prove that their solution depends only on 5 constants. Okay, so what's the general strategy? Remember, we started with the contact supermanifold with some additional reduction of structure group, which we realize as the 1-2 twisted cubic. So a super variety of dimension 1, 2 inside the projectivization of the contact distribution. And by osculation, we canonically obtain out of this 1-2 twisted cubic Lagrangian subspace. But that's precisely the general framework for second order super PDEs. So if you consider the first jet space of map from C22 to C10, that's a 5-4 dimensional supermanifold with a contact distribution. Locally, the coordinates are xi. These are the independent variables, are not differentiating between even and odd variables at this stage. So I runs from 1 to 4. U is the dependent variable, and ui are the derivatives of u with respect to xi. We have the natural Cartan distribution on this space, which is given by the truncated total derivative and the partial derivatives with respect to ui. The contact distribution, of course, has a frame of conformal symplectic orthogonal supervector fields, and the frame I've here, it's precisely such an adapted frame on which my symplectic forms restricted to C takes this form. So look at Lagrangian subspaces of this distribution at a fixed point. They are 4-dimensional, and generically they are of this form here. So it's the truncated total derivative plus some uij partial derivative with respect to uj. The uij are either symmetric or antisymmetric, depending if one index is even or both indexes are odd. In any case, if you look at the Lagrange-Grassmann bundle over M, this will locally have coordinate xi, u, and ui plus this uij. So that's exactly the second order jet space of maps from C22 to C11. Okay, and I will denote it by M tilde. And this also has a canonical Cartan distribution. So a second order super PD is a submanifold of M tilde by definition, and an external symmetry of this submanifold is a symmetry of M tilde preserving the Cartan distribution that sends the submanifold into itself. So now we have to put all these things together. We had our 5-4 contact supermanifold with the reduction of structure group, and that allowed us to select a 1-2 parametric family of Lagrange subspaces of the contact distribution. These were the affine tangent spaces along the 1-2 twisted cubic. So inside the Lagrange-Grassmann bundle M tilde, we have a 5-4 plus 1-2 submanifold, so a 6-6 dimensional submanifold. You play a bit with this submanifold and you realize that the equation it cuts out inside M tilde is exactly the G3 contact super PD that I've written here. So let me skip this fact about the cubic form, because maybe I'll come back later if I have time. But the key point is that we had to compute the external symmetries of epsilon inside M tilde explicitly by a hand computation. And this was facilitated by certain Jordan algebraic construction that, if I have a few minutes, I will tell you later. So this explicit computation tells us that the supersymmetry dimension is 1714. So the upper bound coming from Spencer cohomology and Tanaka-Weisfeiler prolongation is attained. A priori, this yet doesn't tell us that this supersymmetry algebra is G3. It could be filtered deformation of G3, but since G3 and the super Hilbert-Cartan grading of G3, they include the grading element, so the element that acts with eigenvalues given by the grading. Since this element is here, this guarantees us that the symmetry superalgebra cannot be a deformation. It's really graded and it has to be exactly G3, okay? So we have followed this route here by essentially considering the Lagrangian subspaces obtained from the 1-2 twisted cubic. And now we want to go down. So the point is that up here, so on G3 mod P12 on the correspondence space, we have a Cartan super distribution because that is a super PD. And in this case, it has rank 3-4. The Cauchy characteristic space of this distribution, so it means the section of this distribution that sends distribution into itself, is a module for the space of super functions, and it is non-trivial. It is indeed 1-0 dimensional. You have an even super vector field that generates this space. So you want to quotient epsilon by this 1-0 module. And what you will arrive to is epsilon bar, which is now, remember, epsilon was 6-6 dimensional. So we go to 5-6. And we also push the Cartan super distribution down. So from 3-4, we go to a super distribution downstairs of rank 2-4. Okay, so we have followed this route, and one realizes that epsilon bar is exactly G3 modulo P2 endowed with the Cartan super distribution associated to the super Hilbert-Cartan equation. So also in this case, we already know that the symmetries include something of dimension 1714 by maximality coming from the Spencer cohomology computation I showed before. this tells us that the bound is attained, and again, the presence of the grading element guarantees that the symmetry superalgebra is not just deformation, but it's exactly G3. Okay, maybe I'll say a few words about how to compute explicitly these symmetries. So let's go back to this osculating sequence of affine tangent spaces to the 1-2 twisted cubic, and such that V0 is the line to the highest beta, and V1 is our 2-2 Lagrangian subspace. So consider the associated graded vector space to this filtration. Remember, these were obtained by repeatedly applying f-1, which is abelian, right? It comes just from this one grading. So that means that we have surjetic maps from the symmetric algebra of f-1 to this graded vector space. So in particular, my components of the graded vector space are quotient of skf-1, and I can bring the product of the symmetric algebra on f-1 to a product on graded of V. So we get a Z-graded associative and supercommutative superalgebra structure. Here I'm just writing the generators. So here I'm actually writing the elements of f-1 and its symmetric powers that, when applied to here to x cubed repeatedly, give me the elements in n0, 1, and 2, and n3. So if you look at n1 tensor product n2 in 2 and 3 from this relation, you see that this is non-degenerate. So this is non-degenerate, so n2 is the dual of n1, and if we consider the product n1, n1, n2, this becomes something n1, n1, and 1 star. So this gives us a cubic form on n1, and it's supersymmetric. If you fix a basis, let me just not to overload the notation, I want to call this n1w and y1, i5, and a6. I'll call it w1, w2, and w3. So this cubic form is given by this expression where lambda is an even parameter and theta and phi are odd. So we have our cubic form at our disposal. What is this cubic form? That's actually the cubic form of a cubic Jordan superalgebra. So if you consider this product here, you actually have also a unique up to multiple duality, equivariant duality of n1 star with n1. So this object here can also become a product, and this gives us a simple Jordan superalgebra structure on n1 called the Kaplanski superalgebra. So this is a cubic superalgebra, cubic Jordan superalgebra, and the cubic form we obtain is exactly the form associated. Okay, so the idea why this help? Because,
okay, Andrea?
Yeah. Yes? I don't hear you.
Fan, you're muted.
I say just 5 minutes more, okay, Andrea?
Sure. Yeah, I'm finishing now. Yeah. Okay. So the idea is that the G3 contact super PD, so our correspondence space here, can be parametrically described inside the Lagrange-Garmans bundle in terms of this cubic form. So this extends to G3, a formula obtained by Dennis Day in 2018 for all the exceptional algebras, and the fact that the cubic form satisfies particular identities coming from the Jordan algebraic structure, that's crucial for the explicit computation of the external symmetries of the G3 contact super PDs. Otherwise, these will be very complicated symmetries, but the Jordan algebraic structure gives a hand in a way. Okay, I won't say anything about curved G3 supergeometries. It will take me too much time, but I would like to finish with a recent result that I obtained with Boris and Dennis. So there is a procedure in filter geometries to construct canonical parallelism that dates back to the work of Tanaka in the 70s, and it was refined and highly simplified by Zelenko in 2009. So since one of our goals is to push the theory of parabolic supergeometries forward, we decided to establish a similar result in the context of supermanifolds. So Tanaka's original construction is rather complicated, but the simplification of Igor Zelenko allows for more easy modifications. For example, you use it in a context of K-non-degenerate CR manifolds. And also for us, it was more amenable to be generalized to the super case. So the result is the following. If you start with a supermanifold M and a superdistribution D, which is strongly regular in the sense that it's not the kind of superdistribution that I explained at the beginning, okay? I'm not allowing such distribution here, okay? And assume that the prolongation of M of the symbol is finite dimensional, then it's possible to construct a fiber superbundle over M, not necessarily principal, of dimension equal to the dimension of the prolongation, and endow with an absolute parallelism, such that if you have an automorphism of your underlying geometric structure, this leads canonically to an equivalence of the parallelism, and conversely, if you have a diffeomorphism of P that preserves the parallelism, this can be pushed down and gives you an equivalence of your underlying geometric structure. So this implies that the infinitesimal symmetry superalgebra of MD is bounded by the dimension of G. And this was already a result which I kind of implicitly stated when I was speaking with speaking of Spencer cohomology, but in that case I was implicitly referring to locally transitive geometries. If you go out of the locally transitive framework and you want to deal with intransitive geometries, then Lie superalgebra theory is no longer sufficient, and you need this geometric construction that tells you that the supersymmetry bound dimension is still given by the dimension of the maximal prolongation. And okay, if this bound is obtained, then locally and up to the formation, the manifold we started with is our standard model given by the exponentiation of the negative part of G and the distribution corresponding to G minus 1. I think I'll stop here.
Yes, thank you very much here, Andrea, for very impressive work. So that's a really very big work, a lot of computation. And I mean, that's that you are first to extend such kind of the did you first extend this? I mean, that's I know I hear the notion of the supermanifold, superalgebra, but super PDE. So I didn't know that super PDE also important in physics.
Sure, yeah. A physicist study a lot of super PDEs, different kinds of them. For example, in last years, a lot of super conformal mechanics in one dimension has been studied, and that corresponds to different contact gradings of G3 and F4, or of G3 and F31. So G3 has also not just the contact grading that I have considered in this lecture, but it has also another contact grading where the G-1 is purely odd. And so physicists considered superconformal mechanics they don't formulate these in these terms close to parabolic geometries, but one of our working projects is to understand if the super PDEs they obtained are also obtainable from a more let's say conceptual in a way that can be reproduced also in other contexts in terms of parabolic supergeometries. Yeah. So yeah,
So that you are first to extend how to say parabolic geometry. That is a kind of a specialty here in Czech Republic to super parabolic.
Yeah,
you can think that there's a lot of open.
Yeah, we are planning to do that. We are planning to do that. It has several subtleties. For example, this one of the first problems is that this constant theory harmonic theory is not available. That's an algebraic problem. Even proving this theorem that is here in the last slide, in the super case, it requires a lot of technicalities here and there, because as I said at the beginning, in the super framework, things are not determined by the values at points. So in the classical setting, many times you can give formulae which are supposed to be tensorial formulae, and you specialize them at a fixed point. But this you cannot do it in the super framework. So this means that even some formulas which looks nice and compact in the classical setting, they become more complicated when you try to extend them in a tensorial way to the super setting, because you cannot just specify a point. Yeah. So
yes.
So
thank you very much. Yeah. So is there any question more? Or maybe Andrea, you want to add something more?
No, I was just reiterating these points. No, I was just reiterating that that there are both some subtleties from the algebraic and the geometric point of view that need to be settled to extend the parabolic theory. Yeah. Maybe I'll stop sharing if that's okay.
Yes, so Justin, you have a program to do further such kind of extension from the kind of parabolic geometry to super sitting, right? Or no?
You mean other geometries?
What is the next step after this work?
Next step is to generalize this parabolic geometry to the super setting and try to understand if so we already had some progress in understanding if these super conformal mechanics can be understood as parabolic geometries, parabolic super geometries. Because the construction of
very natural,
the construction of Lagrangians coming from in this context of the supersymmetric Lagrangians are really complicated and involved. So we believe if this can be understood in terms of parabolic supergeometries, also the construction of Lagrangians should be easier, hopefully.
Yes. So very congratulations. That's nobody figured out to do it before, or maybe that some people figure out, but that's very complicated. Yeah.
Well, we haven't yet too, but okay. Yeah.
Okay, so if there are no more questions, let us thank the speaker again.